In this lecture, we're going to discuss a little bit about the nuclear chemistry. And nuclear chemistry started with the nuclear radioactivity. That is a spontaneous emission of the radiation from the nuclear reaction. And I like to point out here is the emission of high energy particles. Those particles could be like electrons, nuclears, and sometimes it can be photons as well. Nuclear reaction is a reaction that can change an atom nucleus. And I like to compare this nuclear reaction against the chemical reaction we have discussed so far throughout the entire academic year, including Chem 1 class. The nuclear reaction basically is focused on the nucleus, while the chemical reaction pretty much focuses on the valence electrons that's outside the nucleus. As a nuclear reaction is going to make a change in atom's nucleus, if the proton has got a change, let's say losing or gain a proton, it definitely changes the identity of an atom. In other words, this reaction could generate a new element. While a chemical reaction is a change in the number of valence electrons or electron configuration of an atom, it does not involve the identity of such an atom. The nuclear reaction can happen by the different isotopes, even though they are from the same element. That is what happened for a nuclear reaction. So for example, everybody probably understands like a uranium-235 that undergoes nuclear fission reaction, but another isotope from the uranium-238, is totally different. It does not undergo nuclear fission reaction at all. Of course, it still undergoes the nuclear radioactivity, but it is going to the different paths, different nuclear reactions. But for the chemical reaction, regardless the isotopes, as long as they are in the same element, they undergo the same chemical reactions. In other words, they have the exactly same chemical identities. For the nuclear reaction, the rate and the kinetic speaking, so the rate of this reaction is independent of temperature, pressure, if there's gas involved, or the catalyst. But for the chemical reaction, however, the rate of the reaction actually depends on such things like temperature, pressure, and catalyst. And there are a couple more that is unique for the nuclear reaction. That means the reaction is going to be the same of the atom or the isotope regardless what state that atom is at or form. So for example, if we talk about a nuclear fission reaction like uranium-235, as long as we have uranium-235, it doesn't matter whether it's going to be pure or in the format of compounds. It doesn't matter whether it's going to be the oxides, the fluorides, chlorides, it doesn't matter. It is uranium, the atom, the nucleus of this atom undergoes the nuclear reaction. It has nothing to do with what state that the atom is in. One other thing, much greater energy release. Basically, we talk about at least 10 or sometimes 100 more intensive energy output for the nuclear reaction. So that is how, so nuclear reaction could be very dangerous and very destructive. So that's why we are very worried about the nuclear weapon in this world. A big class of these nuclear reactions is called radioactive decay. Speaking of decay, that means that something has been emitted. According to the history, we had alpha decay, beta decay, and gamma decay. And for alpha decay, it is the emission that we see the helium atom coming out of the nucleus. So for example, if we have uranium-238, and we are interested in what is that going to be after this atom releases one helium nucleus. In nuclear chemistry, we do not call nucleus anymore. We call this as nuclides, nuclide. And we follow the notation we learned in chapter 2 for isotopes. So here we use the full notation. That means not only we need to write the chemical symbol of such element, and also we need to help you to understand that there's a mass number and atomic number. Sometimes we prefer that as a charge number for some very simple particle. Remember, 92 as the atomic number of uranium, indicating there are 92 protons in the nucleus. Everybody understands proton is a 1 unit positive charge particle. So we can relate atomic number with the charge number later on as we discuss for this radioactive decay. Well, let's go back to this question. What is the other product for this reaction, what we call alpha decay? In other words, how should we be able to balance this nuclear reaction? When we try to balance the nuclear reaction, one thing that we need to know about is we have to calculate the total number of mass number from the reactant as well as the total number of atomic number. And total atomic number from the reactants. It doesn't matter how many reactants there are, we just simply add their atomic numbers together as well as atomic numbers together. We're going to do the same thing to the products as well. We're going to add all the products with their masses number and atomic numbers together. The goal here is to find a way that we can make the total mass number and the total atomic number equal on both sides. That is our goal. That is our goal in balance the nuclear reaction. And by the way, that is also the only task we need to understand and we need to master from this chapter. The rest is pretty much for your knowledge only, for your information only, but this is the must, how we should be able to balance a nuclear reaction in this chapter. Remember, the total atomic number and the total mass number should be equal on both sides when we add those reactants and products all together. Now, let's look at this reaction. Remember, alpha particle actually is the helium nuclide, so I'm going to replace that alpha with the helium. Now let's see what do we have as a mass number and atomic number for our second product. There's only one reactant from the left. Now we understand the total atomic number, or the total atomic number must be 92, or the mass number must be 238. If you look at the mass number here, 238 should be equal to 4 times the mass number of another product. That means 234, because 234 plus 4 equals 238. Speaking of atomic number, the total atomic number from the left is 92. Our second element must have an atomic number of 90 in order to have the atomic number adding up equals 92. All right. So once we realize the mass number and atomic number of this product, we can go ahead and check the periodic table, and we find out number 90 element is Th, thorium. That is how we determine the affinity of the element. We have to get it once we know the atomic number of such product or that species. But nevertheless, remember that is our goal of this chapter. Know how to balance the nuclear reaction, and that is a criteria for us to balance the nuclear reaction. Total atomic number and the total mass number must be equal on both sides. Okay, that is about the alpha decay. And the beta decay is also called the beta radiation or beta emission. That is the emission of an electron from the nucleus. This is how we write an electron. Electron has pretty much a zero mass, because electron, although it does have mass, it only about 1/2000th of mass of a proton. In other words, compare the mass against the proton and neutrons, so we can basically ignore. That is the reason why we put 0 as the mass number of the electron. And remember, we said we can relate atomic number to the charge, because that also represents number of protons. Everybody knows proton is positive charged particle. As an electron, it carries negative charge, right? So that's why we put -1 as its so-called atomic number of the electron. So I just want to remind you, this atomic number can also be referred as a charge of some particles like electron. Well, where does the electron come from? The nucleus. A decay of a neutron. The neutron actually can split into an electron. Now, what we have to do is try to figure out what is the other product of this nuclear reaction. Remember, total number of mass number must be the same on both sides. We got a 1 mass number from the left, 0 plus 1, so the mass number of a second product must be 1. And if we look at atomic number, Z here, the total Z on the left is 0, and the atomic number or the charge of our second product must be +1, so that +1 plus -1 equals to 0. So it's 1, 1, and that is the proton. Okay. Because proton, we understand, has 1 unit of a mass, atomic mass, and also it does carry 1 positive charge. Of course, you can write it as hydrogen if you want to, because hydrogen for its nucleus, or we call it for its nuclide, it's just a proton. The third decay, before we talk about it, and I like to talk about something that you probably heard about, positron decay. Positron is the antimatter of the electron. If you look at the notation here, you realize it's also the E as an electron. It carries the exactly same mass number as the electron, only for positron, it is a +1 charge instead of a -1 charge as from the electron. It happens, but not as popular as a beta decay. For positrons, it's very difficult to measure, to observe, because later on we'll talk about what is going on, what happens with the positron when it meets its antimatter electron. In order to have the positron, it is now the turn of proton. So it seems like positron decay is the reverse reaction of a beta decay. So the proton will become the neutron after emitting a positron. Only in this way we find that the total mass number will be the same on both sides, and the total charge or atomic number will be the same. Will be equal to each other. So positron is what we call in nuclear physics the antimatter or antiparticle of the electron. Antimatter does not quite exist in our real world, because the moment that the antimatter comes out and it will react with the matter, the corresponding matter in this real world, and start to initiate a nuclear reaction. Another decay is what we call the gamma emission. Gamma emission, that means gamma as a photon, the gamma ray as a photon emitted from the reaction. As a matter of fact, it occurs quite often for most of radioactive decay. The reason for that is, I would like to remind you, this radioactive decay is also part of a nuclear reaction. Nuclear reaction emits a high energy particle, including photons. So that is the reason why gamma is the photon with a high energy. And another way for us to see the gamma emission actually is annihilation of a particle and its antiparticle. So for example, positron reacts with the electron to form photons. So that is the reason why positron is very difficult to capture. Because just imagine, if we have this setup in a vacuum, unless it's absolute vacuum, once there's a substance in a vacuum or atoms in a vacuum, no matter how small amount it is, there are always going to be electron. The electron will annihilate the positron if that element releases or the isotope releases such a particle, then gives us the gamma ray. So a lot of people can think actually the gamma emission is the isotope actually releases positron, then it reacts with the electron, so that it gives up the gamma ray. But this is just like a pathway, a guesswork. Okay? The pathway is something that we have discussed in the kinetics in chapter 14 already. All right, so as we talk about this many nuclear active decay, so let's summarize a little bit, especially when we try to write up the nuclear reaction regarding those decays. As speaking of process, if we have alpha decay, one of our product that is emitted, or we call emission, is a helium nuclide. All right, so according to helium nuclide, so we recognize there's going to be 2 protons and 4 as its atomic mass or mass number. In other words, this helium nuclide has 2 protons and 2 neutrons. That means for the second product, that means the decay, the product of the decay, in their nucleus, their nuclei, there must be 2 less from the atomic number and 2 less in the number of neutrons. In other words, that are going to be 4 less in atomic number. For beta decay, we have the symbol of 0, -1 of electron or 0, -1 of a beta, of a so-called, we call it a beta particle. There's no change, of course, of mass number. However, 1 neutron has been converted to the proton. In other words, there's going to be +1 in atomic number of that element, and number of neutron is going to be 1 minus. That definitely is one of the reaction that can generate new element, just like the alpha decay. Speaking of a gamma emission or gamma decay, there's nothing changed because it's a photon. It doesn't have mass, it doesn't have charge, so Za and number of neutron doesn't change at all. As a positron decay, remember for positron, there's going to be positive for its charge. That actually comes from a proton. Proton being a reactant, it disappeared, so our product will suffer 1 loss of proton in their nuclide and gaining 1 neutron as a result. All of these is what we call the nuclear radioactivity. And there's also quite a common nuclear radioactivity is what we call electron capture. That happens very commonly for a large nuclide or for the atom with many, many protons. In the chemistry world, that will quite happen to those elements in the 7th period. The reason for that is, first, there are a lot of protons in the nucleus. Second, there are so many electrons flying around the atom. I'd like to remind you, for electrons closer to the nucleus, it becomes more stable. In order to be more stable, it has to move very fast. In a very limited space, moving so fast, it is quite easy for electron to hit the nucleus. Just like it is quite easy for a bug hit on our car if car moves very fast in the summer. In this way, proton will react with the electron from the inner shell and a neutron is produced. And this time, it only emits X-ray. Why X-ray? Because if we have electron in the first principal shell going down to nucleus, this is the energy level for X-ray, photon. Once we investigate the nuclear radioactive decay, we find out pretty much all the decay follow this rate law. And I hope you realize the order for this rate law is first order. So this is the first order process. And then there's the one unique feature about the first order process, which is the half-life time. Because half-life time is independent of the concentration of the reactant. In other words, it is independent of the concentration of isotopes. Since it's a nuclear reaction, this rate constant is also temperature independent. It doesn't matter how hot or how cold, decay will occur. It's always. There are some other major nuclear reactions. One of which I'd like to talk about here is a nuclear transmutation. This is a reaction that one element is going to be changed to another. And here I'd like to use this reaction as an example. This reaction is the result of a bombardment of a higher energy particle coming from the sun. In the sun, so we call it solar wind. In the very far edge of our atmosphere, still there's been nitrogen. And nitrogen nucleus will capture that fast-moving neutron from the solar wind and will start a nuclear reaction. We know the second product of this reaction is a hydrogen atom. Now let's see if we can figure out the first product. Remember, in order to balance the nuclear reaction, the total mass number must be equal on both sides. From the left, we have a total mass number, 15. That means for the first element here, first product here, the mass number must be 14. 14 plus 1 equals 14 plus 1. The total atomic mass is 7, 7 plus 0. And since we already got a proton, which is a hydrogen nuclide, and for our element here is 6 as its atomic mass. Atomic number, I'm sorry, Z. Which element has 6 as its atomic number? Carbon. As a matter of fact, this is the source for carbon-14 on our Earth. On Earth, we do not have carbon-14. Carbon-14 actually comes from pretty much outer space. So once the new nitrogen reacted with the fast neutron to form carbon-14 atom, this carbon-14 atom will react with oxygen to form a carbon dioxide, which is much more massive, sinks down all the way to our atmosphere. And since it's carbon dioxide, so the photosynthesis is going to our biosphere. So that is the reason why every one of us, every living being on Earth, is some kind of radioactive because of the carbon-14. As long as we live, because we take food, which is made of carbon, of course, containing carbon-14, so our concentration, so-called concentration of carbon-14 is pretty much remain the same as long as we live because we're taking food. Once a living being is dead, stop taking carbon-14, then carbon-14 is undergoing decay. This decay will change the concentration of carbon-14. And of course, according to the law of radioactive decay, so we realize it is a first order reaction. So the half-life of carbon-14 to decay is somewhere around 5,500 years. That means for every 5,500 years, the concentration of carbon-14 in the dead body will drop by half. And it's going to drop another half down to a quarter for, so it's 11,000 years, on and on and on. So that's why we have carbon dating, because once we measure just how much of carbon-14 is in a fossil of a dead body for a long time, so we can actually trace back just how long ago this living being has lived. That is how we traced back for dinosaur and we realize dinosaurs exist on Earth 62 million years ago, at least. Well, another type of a nuclear reaction, this one, I think you guys know pretty good already, is called nuclear fission. And here I'm going to use uranium-235 as an example. Uranium-235, after absorbing one slow neutron, when we talk about one slow neutron, that's probably everywhere in this world. So once it's absorbed that slow neutron, it becomes uranium-236, and then it undergoes nuclear fission reaction. Nuclear fission reaction, that means this nucleus of uranium-236 is going to be cut in half, or maybe 3, or maybe more. Fission, that means cut, right? So it's going to be cut in pieces. So in our example, we have a krypton nucleus and a barium nucleus. But when we add up those atomic mass, so the mass number and atomic numbers all together, we find out that from krypton and barium, 36 plus 56 is 92. Atomic number is equal on both sides, but we do have a problem with mass number, because 91 plus 142, it will be 233. So we must have the third particle that can make up a 3 unit of mass number. And I'd like to remind you, this particle shouldn't carry any charge. That would be, you got it, okay, neutron. This reaction will generate 3 neutrons. And once it's a reaction, remember it comes from nuclear reaction, those neutron moves pretty fast, as we call it fast neutron. And once this reaction generates 3 fast neutron, this fast neutron will be absorbed by another 3 uranium-235 and generates 9, then 27, then 81, on and on. So that is why we call it chain reaction, because it's going to the exponential. So that is why in a very short time limit, this reaction becomes out of control. So we call it chain reaction. It is not just uranium-235 that can undergo such a reaction. A lot of other isotopes, like plutonium, Pu, undergoes pretty much the same way for nuclear fission. And the common characteristics about a nuclear fission is its chain reaction. Captures in one slow neutron, returns with 3 or more fast neutrons, and get this reaction going in an exponential way. For most of nuclear fission reactions, for example, uranium-235, there is a critical mass. That means as long as we have this piece of isotope within the critical mass, even though there's a slow neutron flying around, it does not initiate the nuclear fission reaction. Only the mass matches or greater than the critical mass, a chain reaction starts. So that is the reason why, so for atomic or nuclear weapon, atomic bomb, we can store it in a very safe way. So we don't have to worry about nuclear reaction as long as we take those uranium-235 apart, because only combined, once they reach the critical mass, there's going to be the reaction. So that is why when we threw the bomb in World War II to Japan, we got 2 or more small pieces for uranium-235, and only after the explosion we put all pieces all together and reaches the critical mass, a nuclear fission reaction takes place. And you may wonder why we have so much range about the critical mass. That is because, remember, for the nuclear fission reaction, as long as the uranium-235, it doesn't matter whether it's going to be the purest form as element or as a compound. Remember, nuclear reaction is independent of the state of the isotope that is in. So that is why we start to see the range, because of the purity of uranium-238 we have. Once we have the technique or technology to make a more purified uranium-238, the critical mass decreases. In other words, we can put a multiple nuclear head in our missile, ICBM. So we can put as many as 10 or 12 nuclear warheads in there, because we have a technology that it can make those warheads, those critical mass dramatically down to like a 15 kilograms. Another reaction, nuclear reaction, is called nuclear fusion reaction. As a matter of fact, this is a reaction that gives a life everywhere on this earth, because this is a reaction our sun is carrying out at this moment. For nuclear fusion, that means 2 nuclei or 2 nuclides. That would be the correct term in nuclear chemistry. 2 nuclides fuse together to form another new one. So in our case, 2 hydrogen nuclei forms a deuterium. Excuse me, with 1 positron. The deuterium will keep react with the proton to form an isotope we call helium-3. That is an intermediate. According to this most popular pathway that's been proposed for nuclear fusion, helium-3 is going to react with itself to form helium with 2 more protons, or the helium-3 will react with 1 proton to have a helium and 1 positron. And this whole thing actually supports the sun by giving up so much of energy to the space, or any stars. One thing for us to think about this nuclear reaction, we realized we start with the hydrogen atom, proton, or deuterium. They are environmental safe because we have them in our Earth. And once the reaction is done, after the energy is emitted, all we have left is helium. No nuclear waste, no nothing. So this reaction, nuclear reaction, actually is something many scientists searched for as another source of energy source. We got hydrogen everywhere, water. That's however many of hydrogen atoms you want, right? Deuterium. Okay, so once we have this reaction started, we have enough deuterium. So deuterium is no longer the problem. But in order to have this reaction to take place, we have problems. It requires some temperature and pressure, just like the sun. So as you can see, temperature is in the tens of a million, and pressure is in hundreds of million atm. So that is going to be very or extremely difficult to have this kind of reaction occur on Earth. But right now, at this moment, the certain groups of physicists around the world were to form the league. It's called the International Thermonuclear, whatever. It's called ITER, I believe. I forgot the other two words standing for. So they formed a league and working on this process, try to have this nuclear fusion reaction under control. The last report that I ever came across was from China. Actually, that comes from the college I graduated from. They claimed that they conduct a nuclear fusion reaction for 100 nanoseconds. You may think that 100 nanoseconds. How long is that? That could be very important because remember, this nuclear fusion reaction generates so much energy. And 100 nanoseconds probably is a good time for us to initiate and stop the reaction so that the energy can be absorbed without causing any other problem like accidents. And of course, I believe the goal for people have this nuclear fusion reaction control is somewhere in a second or millisecond, because that will give us enough energy to convert to electricity, so on and so forth. But that is still have a long way to go. For the hydrogen bomb, we understand we use hydrogen, but we do not use the hydrogen atom. We use the two isotopes of hydrogen. One is called deuterium, and the other one is the tritium. Tritium is the hydrogen isotope that has 3 neutrons in its nucleus. Deuterium, 2 neutrons. Once we have this reaction to take place, and then it gives a helium and the neutron. But just like the other nuclear fusion reaction that takes place in the sun, it requires high temperature and high pressure. In order to initiate such a reaction, there must be atomic bomb first to provide such high temperature and in some space that can provide the high pressure that is high enough to initiate nuclear fusion reaction. But before we leave that slide, I would like you guys to understand this helium-3. So it's quite obvious, if we have helium-3 according to this path or mechanism of nuclear fusion, we can get nuclear energy quite easy and quite cheap if we can find a source of helium-3. Of course, there's no helium-3 on Earth, but it has been estimated that there are about tens of thousands tons of helium-3 in the moon, in the surface of the moon. The reason is, over the billion years of solar wind, the soil on the moon actually absorbed certain amount of helium-3 isotope. It has been estimated that in order for the United States up and running, all we need is about 11 tons of helium-3. So that is the reason why a lot of countries want to set up their foot on moon, not just like 1960s, but for colonization, try to grab the helium-3 from the moon and transport it back, so that if we have the technology to control the nuclear fusion reaction later on, we can have this thing done. Or later on, if you want to travel through the space, stop by the moon, got the fuel up with helium-3, and they will support us for a very, very long time. Well, enough of that story about helium-3. Now let's look at the nuclear stability. Because when we look at the periodic table, we realize that most radioactive elements occurred pretty much at the end of a period 6 and entire period 7. Those are the radioactive elements. Radioactive means their nuclei are not stable. So, is there anything that we can learn from the stability of those elements? One thing for sure, for the light elements, starting with the hydrogen, the ratio of a neutron and the protons actually can become quite important guideline for us to discuss. For example, hydrogen atom. Okay. And there's one proton. Because it's all a proton by itself, so there's no neutron required. But once we deal with helium, now we start to see equal number of neutrons and protons. In other words, that ratio is going to be 1. And that also applies to the boron, carbon, nitrogen, oxygen, fluorine, neon, you name it. So for these light elements, when we say light elements, we're talking about atomic number somewhere less than 20. For elements like these, the ratio here is roughly 2:1. So as we can see, if we draw the red line here for the ratio, and we start to see the distribution of the stable isotopes of all these elements, which is we call island, so island of stability. Amazingly, this is the area, the island, where we do not find any isotopes yet or element yet, because we're talking about atomic number that's in the neighborhood of 110, 120, and that is the super heavy element. But it has been predicted that if we can find that element in that island, that element should be extremely stable. Maybe somebody even said it doesn't have any radioactivity anymore. And just like the light element. This is something that's quite interesting, and people are still searching. And as we look at this island of stability, we realize the ratio of neutron and proton increases as number of proton increases. Starting for the elements that are greater than 20, for its atomic number, the ratio is somewhere between 1.15 all the way up to 1.52. So that's why you see this thing start deviated from that red line and going upwards, because the slope gets higher and higher. For the elements that has the nucleus greater than bismuth, nucleus is no longer stable. Decay will take place. The reason for that is there's going to be too many protons and neutrons, and the nucleus becomes unstable. So that is why every nucleus after the bismuth undergoes nuclear reaction, some sort of nuclear reaction, either alpha decay, beta decay, so on and so forth. And it also turns out, as evidenced by the abundance, the isotopes with an even number of atomic number becomes a lot more stable than those with the odd atomic number. For example, Nitrogen is something very strange in the solar system among the planets. But there's going to be more abundant elements like oxygen, carbon, right? Neon, helium, so on and so forth. And so in general, so element with odd number of atomic number usually has a much lower abundance in this solar system than elements with the even atomic numbers. When we look at the periodic table, not surprisingly, half of the elements in the periodic table will have both protons and neutrons in even numbers. I'd like to just simply to remind you. Okay, so we can have half of even number, the elements with the even number of atomic number, because the rest is going to be odd, right? 1, 2, 3, 4. So when we count, there's all going to be half and half in even odd numbers. But for those pretty much all even numbered atomic elements with even atomic number, pretty much have the even number of neutrons. So this is something that's quite interesting. And once we have the number of neutrons and or the number of protons falling into this series as 8, 2, 8, 20, 28, 50, 82, this is what we call a magic number. The nucleus becomes exceptional stable. That means extremely stable. Why? Nobody knows. Okay. And we can find out for Z equals to 2. That's helium, right? And number of neutron, 2. So helium is one extremely stable nucleus as well as extremely stable atom as well. 8, that's oxygen, right? And 20, that will be calcium. 28, that will be the element of nickel. You should realize what 82 is. 82 is lead. So lead actually is the last element with a stable nucleus. Bismuth, okay, that could be 83, but that has to come up some arrangement in neutrons to make it stable. Why follows magic number? Nobody knows so far, but this is what we have observed. Once we have atomic number that's greater than 83, that means the number of protons greater than 83 in the nuclide. For the most stable isotope, they must have the number of neutrons slightly deviated from the magic number. And that is a statement we learned from the higher level of chemistry class, but I just listed it out for your information. That's it for chapter 25 I like to discuss. But I still would like to use 20 to 25 for your time to talk about where the elements are from. And that actually is the masterpiece done by a bunch of big name physicists. A masterpiece that got a multiple Nobel Prize in physics. And that theory, after combine all of these masterpieces together, is called the Big Bang theory. Not only this theory gives us the view how our universe is being formed, and as a byproduct, it actually explains just how the elements are formed. The story starts with this particular date, May 29th, 1919, because in the south part of Africa continent, there was a sun full eclipse. Why this particular eclipse? Because people want to know whether we can actually see a star that is being blocked by sun. As a matter of fact, we did. What does that mean? It means light actually curved itself in its pathway. Light does no longer go straight around the sun. It curves a little bit. It curves a little bit. And what theory can actually explain the whole thing? General theory of relativity from Albert Einstein. In his theory, Albert Einstein said, speed of light is the speed limit of everything that exists in the universe. The universe he defined. So that is why I said observable universe. It is not exactly the universe that we discuss in philosophy. So the universe we can actually see, we measure, we can do anything about, that is the universe. That's physics I would like to refer. Now we have a speed limit. That means nothing can surpass the speed the photon travels. All right. So once we have this established, Einstein gives us a beautiful equation, so famous it becomes, okay, the equation for everybody. E equals to mc squared. That beautiful, simple equation connects mass and energy of the light altogether, or the wave altogether. From that equation, we now understand mass can convert to the energy for the light, and in theory, energy of the light can be converted to the mass as well. Easy? Not. So far, I don't know how it can be converted from energy to the mass. But I'd like to recall something that we have learned before from Chem 1 class. That is in the chapter 6, I believe, when we introduce another piece of work done by Albert Einstein, photoelectric effect. And in that discussion, we introduced another equation from Einstein, E equals to h nu. Since they both talk about the energy of the light, so we can put them all together. And from that, we suddenly realize for photon, it actually has a mass, as shown in this equation. And equals to h over lambda over c, speed of light. H is Planck constant. Once the photon qualifies for a mass as a particle, remember photon has a wave, okay, particle duality, and once photon possesses a mass, according to physics, the law of Newton, the gravity, and the light path could be deflected by a massive body like sun. So that experiment of that day of sun full eclipse is trying to prove that theory of Einstein's. As a matter of fact, it proved. That is why people recognize that general theory of relativity. But once we have this general theory for relativity, people can draw some horrific conclusion at that time. One is our universe could have an age. Remember, once the light deviates its way or curved its path over a massive body like sun, in our universe, we have billions of stars like sun. Sooner or later, when light starts to curve around this massive body, curved a little bit, and it will form a closed system. In other words, the light will curve back to its original place. So that is why somebody used to joke. We could see our back of our head. The only question is, how long can we live to see that? How long? In a billion years. So, the observation of light can curve actually will lead us to realize the universe that this theory describes is a closed system. So that's why we call it observable universe. How big is this universe we talk about? About 50 billion light years. Light years is a unit of distance that is used in astronomy. That means the distance for light to travel a year. Everybody understand light travels 3.0 times 10 to the 8th kilometers a second. Then we multiply that by year. So that is going to be a huge distance. Well, once this general theory of relativity has been proved, we actually can look even further about this theory or more detail about theory. Another beauty about this theory is the fourth dimension is introduced. Everybody are quite familiar that we are living in a three-dimensional space. But there's going to be the fourth dimension, which is time. So that's why we have speed, right? So the fourth dimension that's been introduced. So how are we going to understand this fourth dimension with a mind of three dimension? With a three-dimensional mind, I'd like to put that way. So that is why people said, according to their theory, if we consider space as three dimension, put it down as one dimension, and put a time as another, so we got a fabric of space-time as shown right here, like a trampoline. All right, so we have the stars, planets, moons. They all have a different mass, and they're gonna make a dent in the space-time web or fabrics. The greater the mass, the deeper the well is, and the bigger the dent it is. And also, according to physics, once they make the dent, there's going to be a ridge around it. As you can see here, it's a ridge. And that is a ridge prevents the planet, if it's far enough, to fall in to collide with the stars. So that's why a star could have planets, because as long as it stayed out of other side of the ridge of this potential well, we call this potential well in physics, and they are safe. All right. So now we realize that we can have a curve, or we call the well, the mass well, potential well, okay, in this fabric of a space-time. And here comes another conclusion, which I like to call horrified conclusion from that theory. I don't know whether you ever watched a movie that was pictured in 1990s called Good Will Hunting. And this film is about a guy, a custodian, worked in MIT, actually figure out a problem, okay, in the math professor's lab or his office. I'm not sure whether that story actually is true, but I do know something very similar to it. That actually is a true story. During World War I, there's a war between Germany and France, or France. And over the period, the war is called the Trench War, right? So I hope that you heard about it. That Trench War lasted a pretty long time, and there's a pastor from Germany army, and apparently he was a genius in mathematics, and he's got interested with Einstein's general theory of relativity, although back then it wasn't proved yet. Remember, 1990 is the year after the First World War. But he was fascinated by the math that a general theory of relativity brings in. So during the study, in that wartime, he found out something very interesting according to the math of that theory. He said, okay, if we have a sun here, because sun has so much mass and so much volume, it makes so much dent. So say if sun after evolution becomes smaller, but the majority of mass is still there, so we call it white dwarf. And such, because sun is smaller, mass is still pretty much the same. That means density is increased a lot. If with a higher density, it makes a bigger dent in the fabric of space-time. What happens if we keep on shrinking the size of the sun? Say the density becomes so high, it has a density of, say, the neutron star. According to the theory, so the dent becomes even deeper. And according to the math, what happens if we have some spatial entity that has infinity of the density, of its density? So high, in mathematically world, it's possible, right? So if we can just say the density goes to infinity, would that actually punch the hole to this fabric? Because it's going so deep, would that be a hole? Just like a trampoline, if we put something too heavy, the fabric breaks, right? So that actually is what that pastor derived from mathematics. At that time, okay, once he found out this horrific conclusion from the mathematics, he sent a letter to Einstein. Of course, Einstein couldn't believe it. And obviously, he thought there's some kind of a mathematical flaw in that pastor's math derivation. But later on, everybody knows, if we have something with that amount of density, it would become the black hole. The black hole, that means it's so black, even, or the gravity is so huge, even the photon cannot escape once it goes into that well, right? Because remember, there's a ridge, so that's why it's going to repel. But once beyond that, going into that ridge, and then light got sucked in. And now, okay, 100 years later, we know that the black hole actually is a very common an entity in this universe. As a matter of fact, black hole exists in every galaxy, even our own. Why Einstein didn't think about it? Because he was good at the math as well. Because he couldn't stand the conclusion of this. Keep to think of it. If we have a black hole, it sucks everything in. That means it's gonna suck everything in the universe into it. Makes sense. Sooner or later, right? If you talk about the universe at the age like a billion years or trillion years, it depends on which scale they want to use. With that period of time, everything should be sucked in a black hole. For example, our galaxy. How come our galaxies still exist, even though we have a massive black hole right in the middle of it? Apparently, people can draw another conclusion. Our universe actually is expanding. While expansion, it offsets the contraction caused by the black hole. How has that been proved? Proved by Hubble. So that is why we used to name a space observatory after him. Hubble telescope in space. All right, it is the second conclusion that make people a lot more interested. Because if we consider the universe is still expanding at present as time goes by, in our mind, we can actually reverse this process, right? Just like we do that in thermodynamics. If a process that is spontaneous, the reverse is possible if we put a lot of energy into it. So the process can be reversed. So what happens if we contract this universe? Think of the other way around. Would that be the limit for us to contract this universe? Of course, expansion comes with the time as the axis. So as we go to contract, time also goes back. Once the time goes all the way back to 0 second, whatever the universe in that point, is the start of our universe. And we just assume that it's going to be an infinitesimal spot. How small it is, people could say it could be just as small as a nucleus. And at 0 second, according to this Big Bang theory, the full name actually is a hot Big Bang theory. At 0 second, I want you guys to watch the density of this substance, this nucleus, and how hot it is. So that is some wonderful number that is beyond our imagination, like a temperature 10 to the 32 Kelvin. How hot is it? That's way beyond our imagination. All right, so as time starts clicking, there's a Big Bang. At the 10 to the 43 second, negative 43 second, just a little bit right after the expansion. So the universe of size goes from nucleus to the size of a grapefruit. Temperature has been dropped by the factor of 10, and we start to see the gravity separated from the rest of the forces. And once into the 10 billionths of a second, all forces start to differentiate from each other, and the temperature has gone down to 10 to the 15th Kelvin. Those forces are the strong nuclear force, weak nuclear force, electromagnetic, and the gravitational forces. And that is what we call the unified force theory. That actually got Nobel Prize, I think, twice. First, okay, and it is quite easy for people to realize that to unify the electromagnetic and the gravitational. And the discovery of these the other two forces actually, I think, got Nobel Prize once. And finally, the guy unifies all four laws, four forces together, got Nobel Prize twice. Why? Because when you look at this form, the formulas, they all look like pretty much the same. Remember that in chapter 18, we talk about those equations. So like K equals to E over negative energy over RT, right? So we have a three equation that's very similar to that format. And actually, we call the four forces that follows very similar format. So people found a way to unify them, and this is how become the part of the Big Bang theory. All right, so after 1 microsecond of this Big Bang, finally we have a protons and the neutrons. 1 second is a milestone of this Big Bang theory because at 1 second it is believed that electron become stable after annihilation of the positrons. And I want you guys to look at temperature here. It's still 10 to the 10th Kelvin. Okay, we talk about tens of billions Kelvin. We still talk about a hot soup, extremely hot soup. At about the 10 minutes, we start to see the atoms, like hydrogen, helium, deuterium atoms. Okay, now let's talk about the years. So after about 100,000 years, finally the universe started to cool down to 100,000 Kelvin. And it's cool enough or cold enough to become transparent to electromagnetic radiation. So that means light actually can travel throughout the space, or electromagnetic radiation, the wave can, EM wave can travel throughout the space. After about 1 billion years, since there are so many of entities, the atoms, okay, like hydrogen, helium, and so they start to congregate themselves because of gravitational interaction. And after 1 billion years, and so this congregation becomes so big, the gravitational from the core becomes so strong, and so the gravitation becomes so strong, and because those atoms become so close to each other beyond the bonds, so it becomes so together and start off nuclear fusion reaction. So that's why when we have stars and galaxies. The temperature of the universe then is about 200 degrees in Celsius. So that means roughly how much? 360 and about 400 degrees Kelvin. After 10 billion years, we got our birth of our own solar system, and the temperature now is in Kelvin. And we believe our universe is still in the process of expanding. The size still gets bigger and bigger. When it's going to stop? Okay. Somebody knows the answer, but I don't, because I'm a chemist, not a physicist anymore. Okay. But this is what the Big Bang theory is all about. Okay, just from Big Bang theory, we understand we have hydrogen, we have helium, and deuterium. And we understand deuterium is an isotope of hydrogen. So basically, from Big Bang theory, we only have two elements, hydrogen and deuterium. And we understand our sun actually conducts the nuclear fusion reaction that, okay, so combine those hydrogen nuclei all together to form the helium. So this is actually the reaction that takes place in our current sun here, and it generates so much of energy. So 26.72 mega electron volts. 1 electron volt actually equals to roughly 100 kilojoules per mole. So you can imagine just how great this energy is. This is actually what happens to our sun like here. Oh, I'm sorry, right here. And of course, you probably know that later on, after 4 billion years or so, our sun becomes the red giant. Okay. And before we talk a little bit about this, I'd like to point out something right here. E plus, called the positron. Nu E actually is what we call neutrino. Neutrino is a subatomic particle. And it is said that it is neutrino that constitute the dark matter in our universe. Because when we weigh up all the stars, galaxies with their masses all together, we find that there's still about 80% of mass missing. That 80% of mass is what we call a dark mass. And I believe it is neutrino that is pretty much responsible for it. Because neutrino becomes so small, so light, as you can see, neutrino does not have a charge, does not have a mass, even lighter than the electron. So nothing actually can stop when it starts to move. So it's very difficult for us to capture such subatomic particles, but we know they're there, along with the other very light subatomic particles. Those constitute the dark matter that weighs out about 80% of the mass of the universe. All right, once the sun becomes the red giant right here, you can see right over here, this is our sun at this moment now. Okay, it becomes bigger and bigger, it's become redder and redder. And once the hydrogen doesn't make up 10% of its total mass of the star, we are into the era of the red giant of the sun. Since the majority component of the sun is the helium, the sun undergoes burning helium. So once the burning helium, as you can see, there's more and more elements start forming. And they start with, okay, so the interval of 4 as the mass number. So helium to the beryllium, beryllium to the carbon, carbon to the oxygen, neon, and magnesium. And of course, as we go into the later and later, and the size becomes bigger and bigger of the red giant, as we find more and more metals, or the heavier metals in the star. And pretty much the last stage before the outburst of the red giant, the stars start burning carbon. This is where the size of the sun becomes so big it engulfs the Earth. And according to the reaction, so the carbon starts to get burned in the nuclear fission reaction. And we can see we have magnesium, and then we can have sodium and the neon. The next process after the red giant that becomes more in the debate. But the general consensus for what happened after red giant is going through, so the star is going through the alpha process. That's very similar to the helium burning, but only this time neon absorbs a certain amount of energy so that it can provide helium as a fuel for the red giant to start burning, to continue burning. This is a reaction that's occurred right before the red giant outburst to become the white dwarf like our sun. So this is basically the fate of our sun. And during that process, not only magnesium can be made, we can have the other elements, so with the mass number +4 in that series, like silicon, sulfur, argon, calcium. Now calcium 40, calcium 40, so calcium is the 44 mass number, titanium, on and on and on. So that is for our sun. But our sun is the average size, actually is more towards the small size of the star. For the star with the larger size or larger mass, like 3 times the mass of our sun, it undergoes something quite different. It undergoes the process we call E process, which is called equilibrium process. According to this process, it will produce the the different nuclei ranging from 22 to 29, centered at iron 26. Remember, iron has atomic number 26. Meanwhile, there's also some model to explain, okay, for the big sun, the massive sun, okay, like 3 or 6 times more massive than our sun. There are also some other process going, like a slow or rapid neutron absorption process. And it also happens at the lifespan of that big star, massive star. During that process, it will form even more isotopes all the way up to bismuth. And of course, and during the process, there could be the proton capture process, so that right before the sun explodes into the supernova, and atoms will grab the protons nearby and to form the new element. This is where we start to see the element with the odd number of odd atom number, like carbon 2, the nitrogen, so on and so forth. And it is our belief that this is the process that generates the bunch of the other half of elements in our periodic table with the odd atomic numbers. And of course, that makes up pretty much the full spectrum of the elements in our periodic table with the various isotopes. As we look at the abundance of elements in our own solar system, we find out hydrogen and helium, they of course has the highest abundance because our sun's right there, right? So 80% of the mass of our sun is hydrogen, 20% is helium, and sun with pretty much the rest of the planet in our in the solar system. So they have the greatest abundance. As we can see that the curve with the lighter color, those curves are the elements, the abundance of elements with the even atomic number. And for those who has the darker line, the line connect those odd elements with the odd atomic number. So that is why in general we see that the abundance of the element with the even atomic number in general greater than the elements with the odd atomic number. The evidence of this atomic number actually proves that our solar system has come from a much larger star going through the helium burning, carbon burning, and alpha process, and P process, on and on. And it is turned out that the lighter elements becomes more abundant than the heavier elements. And of course that makes sense because alpha process or P process occurs right before explosion, right, of the star. And of course there's some exceptions there, like lithium, beryllium, boron, phoron, scandium, because they have quite a good abundance. That means our theory or our model still needs to be fixed a little bit here and there. And also we find out that there's the end right here, and we find out there will be no element with the atomic number greater than bismuth has any more stable isotopes. And all of which proves that our current system actually comes from a massive star after explosion into the supernova. And lastly, I'd like to talk about the nuclear binding energy. And how are we going to calculate the nuclear binding energy? We follow Einstein's formula, E equals to mc squared. So the energy released by the nuclear reaction actually is equal to the mass loss times c squared. So you can have an idea, just say, if an atom loses 1 electron, how much energy is going to be released. A little bit of energy, a little bit of mass actually comes with a huge amount of energy. In other words, there's going to be a huge amount of energy to form, in theory, a mass. This diagram tells us iron actually is the maximum, becomes the most stable nucleus, because iron is either too heavy for the fission reaction or too light. Iron has become too heavy for the fusion reaction, or it becomes too light for fission reaction. So the fission reaction becomes exothermic for lead nuclei, and such reactions like the one I just showed you. Okay, so there's a fusion reaction, or the fission reaction becomes exothermic for the heavier nuclei, like the reaction for uranium-235, as we discussed before. That is the end of this discussion of the chapter 25. And I just wanted to point out a lot of materials discussed here are not going to be in our final exam. The only thing that's possibly in our exam will be the balancing the nuclear equation. Okay, so remember, when we try to balance the nuclear equation, two things must be satisfied. The mass number must be equal on both sides. The total atomic number must be equal on both sides. And thank you, and I hope you good luck and good health for this special period of time.